Hello everyone, welcome to the Introduction to Mechanical and Industrial Engineering course, Make 130. This is another new video of mechanical design. In the mechanical design subject, we're already discussing different topics. Some of these are the machine elements, the most commonly used one. We have discussed this. Also, we discussed the function of each one of these elements like gear, shafts, and bearings, and so on. Also, we discussed some of the commonly found and used transmission system like the transmission of your vehicle or car. Also, we discussed the unit system and their conversion, how we can convert from the American unit system to the international unit system. Also, we discussed the force and force analysis, stress and stress analysis. In today's video, we're gonna continue the other topics which are related to the mechanical design, like the tensile test, engineering materials, dynamics, and factor of safety. Right. So over the previous two videos, actually, we were discussing the stresses, and we were discussing the difference between the deformation, the strain, and the stress. And we said that the deformation, it is not that accurate measure that could be used to investigate how much this material is severely affected by an applied force. We said that the strain is more accurate than deformation. Also, we discussed that the strain by itself, it is not that accurate. It is more accurate than deformation, but there is another more accurate measure, which is the stress. The good thing of the stress that it relates the force and the strain that it was going to generate within the material because of the applied force in relation to the material type. And we discussed even this trick or this game that we discussed in one of the videos, like in order to break this stick, this requires that you should apply a certain force, and the ability of this stick to withstand the applied force, this depends mainly on two things: the size of the stick in addition to the material type. So that's why the main concern of the mechanical design engineer when they design or when he or she design a mechanical component is to find the most suitable size in addition to the most suitable material type that would be used for making this mechanical component to give it the ability to withstand the applied force. So this is the basic idea of the mechanical design. So that's why we were discussing the forces. We discussed the forces and how we can do force analysis. Also, we discussed the stresses that would be generated because of this force. So since everything is related to the material, it is important to know what are the different types of engineering material that we are dealing with as engineers, this known as engineering materials. Also, it is important to know how we can extract some of the mechanical properties that we're gonna use as mechanical design engineer. And this is the objective of today's video, is to discuss the tensile test, how we can do it, and what are some of the common mechanical properties that we are interested with as mechanical design engineer. Also, what are the different types of materials. All right, so as we discussed before, that there is Hooke's law. Hooke's law, this relates the stress to the applied strain, or the applied stress to the strain. The stress, we can determine the stress in terms of the applied force. As we explained that the normal stress, for example, it is the force over area. The shear stress also, it is a force over area or double area in case that would have a single shear or double shear. So what does it mean this? It means that for a specific given force, we can simply calculate the stress, the applied stress or the induced stress. This is the stress that is going to be applied over the material or the mechanical component. So we can simply determine how much is sigma. But in order to determine how much is the strain that is going to be generated because of the applied force, we should have this relation, a constant, which is known as the Young's modulus or the elastic modulus, as we discussed before over the previous videos. This elastic modulus, it is a material property. So what does it mean, a material property? It is something that distinguishes one material from another material. Like, for example, if we're going to say that the Young's modulus for aluminum, it with a certain value, which is around 70 gigapascal. For the Young's modulus for copper, for example, it is a totally different value. For steel, it is a different value. It means that for every specific material type, there is a specific value for the elastic modulus that depend on the material type. So that's why it is known as material property. This is like a name to the material, a special thing that distinguishes one material from another material. So in addition to the elastic modulus, there are lots of other material properties. So this elastic modulus is known as a mechanical material property because we are, as mechanical engineer, even industrial engineers, we are using this elastic modulus especially for the mechanical design application. Also, civil engineers, they are depending and they should have in their design application for structures, they should have knowledge about this elastic modulus, and they should know how they can determine this Young's modulus or elastic modulus for different materials. So generally it is a material properties. Since we are mechanical engineer or industrial engineer, so we're gonna say that this is like a mechanical material properties. But in addition to this mechanical material property, there are lots of other mechanical properties that could be defined or specified for different material. It means that we can specify or distinguish one material from another material depending on a set or a group or multiple mechanical properties that distinguish one material from another material. One of these mechanical properties is the elastic modulus. But in addition to the elastic modulus, there is shear modulus, there is the plasticity limit, for example, or the fraction limit for the material, the ductility, brittleness of the material. There are lots of mechanical properties that distinguish one material from another material. So the objective now is first to know how we can determine this elastic modulus experimentally using an experimental, how we can measure experimentally for a specific material this elastic modulus using a test that is commonly known as the simple tensile test. So we are going to discuss this test. Then we are going to discuss some of the commonly used mechanical properties of material that we are intensively use as mechanical engineer or as industrial engineers. Then we are going to discuss the different types of materials. Alright, so this is like the initial setup or a general standard form of a simple tensile test. So what is a simple tensile test? Simply the tension test or simple tensile test or tensile test is one of the most common mechanical material tests. Like in addition, so the objective actually of this material test is to identify some of the mechanical properties or some of the physical properties of material. Properties of material could be physical properties. If we're going to talk about the mass, the density, these are physical properties of material. We can measure them for different materials. Also, some of the mechanical properties like the Young's modulus, the shear modulus, the Poisson's ratio. So all of these are different mechanical properties. So why mechanical properties? Why we are giving them the name mechanical? Because we are, as mechanical engineer, even industrial engineer, we are using these mechanical properties. Also because we are determining these properties using a mechanical approach, using a machine. We said that anything that is related to a machine is known as mechanical. It will be classified as mechanical engineering, right? So as mechanical engineering in the simple tensile test, we are using a mechanical method to determine some of the material properties. So that's why we give it the name as mechanical material tests. It is a mechanical method. It is a mechanical approach of identifying some of the properties of material. Some of these properties of materials are like the Young's modulus, for example. Again, why it is mechanical? Because we are using a machine to perform this test. But in addition to the mechanical methods or approaches of material testing, we could use chemical methods. So we're going to say that this is a chemical method of material testing. Or we could use, for example, any other approach that depend on physics law. So we're going to say that this is like kind of physical method of identifying the material properties. So there are lots of approaches, there are lots of methods of identifying the properties of material. Some of them are physical, some of them are mechanical, some of them are chemical methods of material testing. Here we are talking about the simple tensile test. Simple because it is kind of a simple, this is the simplest ways of identifying so many of the mechanical properties of material. And we are using a mechanical machine, or we are using a machine, so that's why we got the name as mechanical material testing. So tension test or the tensile test is one of the common mechanical material tests. One of the common things mean that there are lots of other mechanical methods of testing material. We can do like frictional bending of the material. We can do testing like this. This is a simple tensile test. We can do shear. We can test the material with so many other approaches of mechanical methods, using machines also, but the other methods, we are identifying different mechanical properties. But here, the simple tensile test, we can identify one of the most important mechanical property that we can determine as mechanical design engineer is the elastic modulus. So simply, to determine the elastic modulus in this Hooke's law, we said Hooke's law equals sigma equals E epsilon. To determine this E for a specific material, which is a material property, the most proper way is to use the simple tensile test. How it is done? It can be used to determine several mechanical properties. Here we are talking about the tensile test of materials such as the Young's modulus, the strength of the material, in addition to so many other mechanical properties that we can drive or determine by this simple tensile test of the material. How it works, we prepare. For example, let us assume that we are interested in finding how much is the Young's modulus for a steel material. So we're gonna cut, or we're gonna form, or we're gonna manufacture a sample. This is known as the material sample that is made of the same material that we are interested in finding its elastic modulus or its Young's modulus. If we are interested in finding how much is the elastic modulus or Young's modulus for steel, so we have to cut a material sample with this form, with this shape, with this standard dimension that it should be made of steel. If we would like to identify the elastic modulus of aluminum, so we have to cut this material sample from aluminum part, and so on. So it should be made of aluminum, made of steel, made of the material that we are interested in finding its elastic modulus. This is the first step, is just to make and prepare this material sample. Making the material sample itself, it requires a manufacturing method. So that's why part of this course we are going to discuss the different manufacturing methods as well, is how to make this material sample, because this material sample, it should be cut from a specific raw material that is made of steel or aluminum or copper, depending on the material sample, the type of the material sample. Then we have to cut it with these specific dimensions. These are the standard dimensions. So what does it mean, standard dimension? These are the standard shape. This is the standard shape of the material sample. And it is cut with this diameter, which is 0.505 inches. This is in the American system. This double dash indicator is inch, and the gauge length, this is the original length. So the gauge length indicates the original length of this material before the testing, the tensile test. It is 2 inches. And there is like an extended length, which is reduced section to this another length, which is 2.25 inches. And in addition, we're going to have an increase in the diameter at 3/4 inches. And this diameter is going to be 0.505 inches. As I mentioned, this is the diameter of the material sample. So these two parts of the material sample, these are the clamping sides. This is like the sides or the two ends of the material sample that will be clamped into the machine. And the machine is going to do like a tension. It's going to apply, keeping stretching this sample till it will be completely fractured. And this machine, it will be connected to the computer through some sensors. And these sensors, they are going to detect the stretch in the material because of the applied force. So there is one sensor that is used for detecting how much of force that this machine is applying over the sample. And there is another sensor which is known as the extensometer. This extensometer measures the extension in the sample up on increasing the force. So the test, it works in this way. Like we manufacture this material sample, then we're gonna fix it over the machine. The machine has two parts or two sides. Like this is one end of the sample that would be fixed in one end of the machine, and this is the other end of the sample that will be fixed in the other end of the machine. And this is like a schematic representing the simplest form of this machine, that it is like a power screw. This screw, when it rotates, this part, it will be moved. It will be moved down. As this part moves down, there is a force that is going to generate it into this material sample, and this material sample will be stretched. Think of it like it is made of plastic material. So as this part, lower part, this part is fixed, is not moving, but this part is moving down. So as this part of the machine moves down, the material will be stretched. And remember, there are two sensors here. One measures the force, how much of force is generated within this material sample. Another one is the extensometer that measures the stretch, the elongation that is happening in this material sample because of the movement of this platform. Make sense? All of these data are collected. So all of these sensors are connected to the computer, are collected over the computer that do some calculations to determine a curve is known as the stress strain curve, which is similar to this curve. From that curve, we can then print it. And once we print this curve, we can extract so many mechanical properties of the material. So this is simply how the simple tensile test is performed. So it works in this way again, that we prepare a material sample of the material that we would like to identify its mechanical properties. Then we fix this material sample over the machine. So that's why it is a mechanical method of testing. We are using a simple tensile test machine. It is a machine. We fix this material sample over this machine. The machine, it do two things. They apply certain force over the material sample and keep on stretching the material sample till it will be completely fractured. In the meanwhile, there are some sensors that connected to the computer. This computer will do some calculation to extract a figure. This figure is known as a stress strain curve. This figure is known as stress strain curve that gives the stress over the vertical axis and the strain over the horizontal axis. From this figure, we can determine the mechanical component or properties of the material that we are testing. So what does it mean this? It means that for every specific material, there is a different form or a different dimension or shape of this stress strain curve. It means that for the specific material time, for every specific material type, there is a specific stress strain curve. This stress strain curve will be different from one material to another material. Why? Because we are testing a different material, so definitely the stress strain curve will be different. Make sense? Now I'm just going to let you with this video that explaining in detail a real example of tensile testing of two different material samples. One is made of steel, the other one is made of aluminum.
The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 mm and an original gauge length of 100 mm. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 mm. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis.
So it works in this way, like initially the machine applies a certain amount of force. This force at this instant it is 0.41 kilonewton. So this force it is like kind of very small force. So that's why we barely can see a curve. You see this red dash that indicate that there is initiation of elongation. So initially the machine determined the force versus the length. or the elongation. This elongation, it measures the difference between the new length upon applying the force, because once we apply a force, the material sample will be stretched slightly. The length will be slightly increased. It will be slightly increased with a certain amount. So if we measure the new length, negative the original length that is already recorded inside the machine, we can determine how much of elongation that this material sample experienced because of this little small force. So this is how it works. Like initially the machine apply a certain amount of force, so the material will be stretched. Because the force, there is a certain amount of force, so it will be stretched a specific elongation, or will experience a specific elongation. Then after that, the machine have to increase the force further to achieve more or an additional elongation. So to keep on elongating the material, we have to keep on increasing the force. The machine have to keep on increasing the force. So all the time, this is how it works. Like we are keep on increasing the force, so the new length will be keep on increasing, and the elongation as well will be keep on increasing till we're gonna end up with a curve till the material sample will be completely fractured. So this is simply how the simple tensile test is done.
The elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length.
Yes, so as you can see here, the forces keep on increasing, the new length of the material is keep on increasing, the elongation is keep on increasing, the elongation will start from almost at zero, and it keep on increasing in this direction. So this is the elongation. As you can see, we're gonna end up with almost like a straight line, a linear relation. This is not like a linear relation between the force and the elongation in the material sample. This region is known as the elastic region that indicates an elastic behavior of the material. As she just mentioned, this is known as the material elasticity region, or the elastic behavior of the material. What does it mean, elastic behavior? As I'm going to explain this with more detail, it means that if for some reason, if we decided to stop the machine and we remove the material sample length will be restored back again. It means that this elongation will be eliminated and the material will be shortened back again to restore its original length. In this case, the material works like a spring or like a string. A spring, it means that if you try to stretch this spring, it will be elongated with you, right? But once you remove your hand, once you remove the force, the spring will be restored, will return back to its original length. It means that it is elastic. Elastic, it means that it can restore its original dimensions upon the removal of the applied force. Once we remove the force, it will return back again. And this is typically what is going to happen to this material sample at this instant of time. For example, now, if I decided to stop the machine, I remove the material sample length will be restored back to the 100. Now, at this instant, the material length, it is 100.13 millimeters. If I remove the force, this extra 13 millimeter will be eliminated and the material will restore back again its original length, which is 100. When you measure, if I remove the material sample, I try to measure the gauge length or the material length, it will be 100. What about the 13? It has been restored. Why? Because the material is still in its elasticity region, in its elastic behavior. This is what does it mean, an elastic behavior of the material. It means that the material behaves like a spring.
In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be...
So as you can see, we do have like a continuous increase in the force that is proportional with the increase in the elongation. There is like kind of a straight line that we end up with. But at the end of this straight line, we're going to have like a sudden drop and something strange that is going to happen here, right? This point which is the end point of this straight line, is known as the proportionality limit. This is the limit of the elasticity, kind of this material. And beyond this elasticity region, the material will start to yield. Yield is known as the yield phenomenon or the yield behavior of the material. This yield region, it is a transition between two distinct regions or two distinct behaviors of this material. Before the yield region, this is the yield region or the yield point. Before this yield point or yield region, the material will be elastic. What does it mean, elastic? Again, it means that the material behaves like a spring. It means that the material can restore its original dimensions upon the removal of the force. But beyond this point, beyond this yield, the material will not be able again to restore its original dimension. Instead, the material will show a permanent deformation, a permanent increase in the length, and this increase in the length cannot be restored back again. Make sense?
Unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Luders effect. After a certain strain, known as the Luder strain, the force increases again. The material opposes an increasing force against the imposed elongation. It strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner but keeps a cylindrical shape.
So as you can see, she mentioned some keywords that I didn't explain, and I won't gonna explain there, like strain hardening, for example, because this anyway it will be covered with more detail in another course, which is like the material science class. But as I mentioned, the objective here is just to understand what is the tensile test, and there are some of the important keywords like elasticity and plasticity. So as I mentioned, this abrupt or restrained behavior or relation between the force and the elongation, kind of like you don't have the force, almost it is a constant value and the material is keep on elongating. This is known as the yielding of the material. I mean the material is yield, and this is, as I mentioned, the region that distinguishes the elastic behavior from what's coming after this yield is known as the plasticity of the material or the plastic behavior of the material. In the plastic behavior of this material, the material will not restore its original shape one more time. It cannot restore back. It means that the material will show a permanent deformation that cannot be restored back again. Make sense? So as you can see, as we are keep on increasing the force, the elongation is keep on increasing till we're gonna end up like almost, it's gonna be like kind of constant. So we're gonna approach a point which is known as the necking point. This necking point is gonna show a neck. So now, as I'm running the video, your objective is just to keep observing the formation of the neck within the material sample here. Just observe this part.
As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there.
As you can see, the neck has been formed here. It became very thin in the middle, right? This is known as the neck, and this neck, it is conjugate or related or somehow it is gonna take place at this point. This point is known as the necking point, at which the force is gonna be maximum. So this is the maximum force that this material can withstand. Beyond this maximum force, the neck will start to show up or start to form, and this indicates that the material became very weak and the material gets ready to be fractured. And this is what is going to happen after a while, that with this neck, it will be keep on thinning and thinning till the material will be completely cut. So as you can see, the material sample is completely split into two pieces, and this end point, this is the fracture point. So this is the point, this is the end, this is the maximum elongation that this material has been experiencing because of the increase of the force on it. Make sense? And the maximum force is happening at this point, which initiates the formation of the necking as we mentioned. Beyond the yield region, what's on the right of this region, is known as the plastic behavior of the material or the plasticity of the material, and before this region is known as the elasticity of the material or the elastic behavior of the material. There are some of the mechanical properties which are related to the plastic behavior of material that we can derive from the region on the right of the yield region. And there are some other elastic mechanical properties of the material that we can derive from this sphere by testing or investigating the line before the yield region. Make sense? So this curve that we end up with is known as the force elongation curve. Then we can convert this curve into stress-strain curve later by doing some other calculation. Make sense?
In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated.
Alright, so this material sample that we just tested, it is made of steel, and that's why it showed like this yield point phenomenon or this yield point or yield region, it was clearly seen. As I mentioned that this force elongation or even this stress-strain curve, it could be different from one material sample to another material sample or one material type to another material type. So this is the steel, this is the force elongation or the stress-strain curve that we can obtain for steel material. But how about if it is made of another material? Should we obtain exactly typical the same stress-strain curve or force elongation curve? No, it will be different definitely from one material type to another material type. So now I'm gonna give you another example of a material sample that is made of aluminum, and this material is gonna show a slightly different force elongation curve or stress-strain curve. That this aluminum material sample, it will have no yielding point phenomena. It means that this yielding region will not be clearly seen in the force elongation curve. And this is the other material sample that is going to be tested here. Okay? So it's going to be this one. Yeah.
Test, a material without yield point phenomenon is to be tested. In this case, it is a precipitation strengthened aluminium alloy. The test piece has exactly the same shape and dimensions as the specimen in the first test. It is cylindrical, with an original diameter of 10 mm and an original gauge length of 100 mm. After fitting the test piece into the testing machine and panning the extensometer into its working position, the test can start. The initial linear curve in the force elongation diagram again shows the elastic behavior of the material. But this time, the end of the elastic area is not revealed by a sudden drop of force or...
Okay, so as you can see, there is the force elongation relation that is kind of different, right? Over the previous material sample, at the end of the linear relation, there was like a sudden drop or decrease in the force. Then we obtained the force kind of constant over a certain period or amount of elongation or continuous elongation of the material. Then we move to the plastic region, right? It means that the plastic or the yield region that distinguished the elastic from the plastic region, it was clearly seen. But now in this material sample, which is another material type, it is made of aluminum. The previous one was steel. So for this material type, we do have a smooth transition from the elastic to the plastic. There is no yield region There is no specific region that we can identify this is the yield point or this is the yield region of this material that distinguishes the elastic to the plastic. We're gonna end up with like kind of a curve, smooth transition from the elastic region, the linear relation, to another non-linear relation. It means that we are obtaining a smooth transition from the elastic to the plastic region, but there is no specific point that we can say, okay, this is the yield point of this material. Make sense? So that's why this material type is known as a material without yield point phenomena. But the steel, it is a material with yield point phenomena. Why? Because the yield point or the yield region, we can clearly see this yield point within the stress-strain curve or the force elongation curve. Make sense?
Any distinct change. There is a smooth and gradual transition from linear elastic behavior to plastic deformation. In the further course of the tensile test, the force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there.
Okay, so as you can see, we're gonna end up with almost the same way, the same curve, but with the slight changes, right? There is no yield here, so that's why this material type is known as a material without yield phenomena. But the other phenomenon, but the previous material sample, which was made of steel, it was having this yield region was clearly seen, so that's why it is known as material with yield point phenomena. Make sense? Also, as you can see, the way of fracturing the material, it is different, right? The neck here, it is barely formed, but in the case of the steel material, the neck was clearly formed, and then the material has a different way of fracture. So the fracture of the material, even it is a material property, it depends on the material type. The way by fracturing by which this material is going to fracture, it is totally different and distinct from one material type to another material type. So all of these are so many mechanical properties that we can drive through the tensile test, as I mentioned. And the key condition of this machine or this method, it is a mechanical method of material testing. Why mechanical method? Because we are using a mechanical approach, or we are using a machine. This machine is known as the simple tensile testing machine. Alright, so as we showed in these two videos, or this video for these two material samples, for the aluminum case, we obtained that the material has a smooth transition from the elastic region to the plastic region, and there is no specific yield point that we can identify. But for this material sample, like the case of the steel material sample, we end up with the yield point, or the yield region was clearly seen by the sudden drop in the force, and we're gonna obtain like this like odd behavior of the material within this yield region. Then we're gonna move to the plastic region. So this yield point or yield region clearly identify the difference between the elastic behavior or the plastic behavior of the material. So we're gonna say that this material is a material with yield point phenomena, which this one on B, but material A, it is material without yield point phenomena. And this is the stress-strain curve. The question is how we can obtain the stress-strain curve from the force elongation diagram. We show over the video, the machine gave us the force versus elongation. So it gave us the force versus elongation. This is the elongation delta FL and the force as F. So simply, if we divided the force over the area of the material sample, the original area, we can convert this into stress. As we discussed before, we said that the stress, it is force divided by area. And also we define the strain as the elongation divided by the original length. So if we divided every force value, we're gonna end up with a curve. Then we can do some calculations, further calculations over this curve by converting the force into stress. So if we divided the force over the original area, we're gonna end up with the stress. If we divided the elongation, every elongation over the original length of the material, we're going to end up with the strain. And in this case, we're going to end up with a very similar curve, which is known as the stress-strain curve. Then from the stress-strain curve, we can drive so many mechanical components. Definitely in other courses like mechanics of material, material science, you're going to know exactly how you can drive the mechanical components of for a certain material given this is stress-strain curve. In case that you already given this is stress-strain curve, how we can drive the mechanical component for a given stress-strain curve, this will be covered, as I mentioned, in other courses. But here I'm just going to mention one property that we discussed in this course so far, which is the elastic modulus. How we can drive the elastic modulus from a stress-strain curve. This is what I'm going to show you. Make sense? But again, the machine gives us the force versus the elongation. Then we can divide the force by the original area, divide the elongation by the original length to end up with the stress-strain curve. Some machines, and now the machines can simply do this since it is already connected to a computer, so the computer can do this calculation. Even we can extract directly the stress-strain curve from the machine without any further calculation. It means this step of the calculation, dividing the force over area, dividing the elongation over the original length, this can automatically be done by the computer that is already connected to the machine. Make sense? All right, so this is a typical example of a stress-strain curve for any material, whatever it is. It should be we should end up with a very similar curve to this stress-strain curve. It could be different from one material to the other within especially the yield region or this yield point, whatever. Like this material, it has a yield point phenomena. Like there is no smooth transition. This is like yielding region is already shown here. But some other material like the aluminum material sample, as we mentioned, it could have this smooth transition without any yield point phenomenon. Make sense? It means that for all material, almost you could say for all linear elastic material, we're going to end up with the same stress-strain curve, but it will be slightly different from one material sample to another material sample. Make sense? So there are lots of mechanical properties, as I mentioned, that we can drive or extract from this curve. One of these mechanical properties is the elastic modulus. This elastic modulus, which is E, or the Young's modulus, it is the slope of the linear stress-strain curve of this, or the linear relation or the line within the stress-strain curve of the material. We said that this is the yield region, and we can draw like a line here that is slicing this curve into two pieces, into two parts. One part on the left, which is known as the elastic region, and anything that is located on the right of this line, it will be known as the plastic region, that indicate or describe the plastic behavior of the material. So the behavior of the material in the elasticity is different than the behavior of the material in the plasticity, and we are going to explain this with more details. Make sense? But now the yield region, one of the important things of the yield point or the yield region is to identify this region is that it can distinguish between the elastic and the plastic behavior of the material. Within the elastic behavior, we're going to end up with like a straight line, almost a linear line. The slope of this line is going to give us the modulus, which is known as the elastic modulus, which is E, that found in the Hooke's law. We said that Hooke's law equals sigma equals E times epsilon. This is the elastic modulus. What does it mean? Slope from mathematics, any linear relation or any function, whatever it is, it has a slope. And how we can determine this slope, simply your objective is just to find the derivative of this function. It means that if you just calculate, since this is a linear function, the slope of this line is going to be the tangent of this angle theta. So this angle theta, for example, we can draw like a triangle within this region. And if I ask you to calculate the tangent of this angle theta, it will be the opposite divided by the adjacent side of this triangle, right? So the slope of this line, which it should be the tangent of the angle theta, this is going to give us automatically the Young's modulus E. It means that if we printed this figure and we measure this angle and we did some calculation, we find the tangent of this angle, you're gonna directly end up with the Young's modulus of this material, how much it is. So this is simply how we can determine the elastic modulus or the Young's modulus of any specific material from the given stress-strain curve. But in addition to the elastic modulus, there are so many mechanical properties, like the proportional limit. This is one of the properties of the material that distinguish one material from another material. It means that, for example, the proportional limit for steel is different than the proportional limit for aluminum, than copper, and so on. The same thing, the amount of stress, the stress that is next to the yield point is known as the yield stress of the material, and this is a good measure of how strong is this material. So again, the stress that is next to the yield region or the yield point of the material is known as the yield stress of the material. We used to give it a symbol like sigma Y. Y stands for yield stress, and it is a material property. What does it mean, material property? It's something that distinguish one material from another material. Or in other words, steel has a yield strength that is different than the yield stress or strength of aluminum, and so on. So that's why it is a measure of how strong is this material, because in the mechanical application side, we have to avoid moving the material to the plastic region. We have to keep the material all the time in the elastic region. This is an essential requirement to have a good design. If you are required as a mechanical design engineer to design a gear, to design a shaft, any mechanical component that you are planning to use in any machine, whatever it is. So as an essential requirement, if you remember when we were discussing engineering design, there was design specifications. One of the design specifications is the strength of the material. Or in other words, that we have to do the design of this mechanical component in such a way that we have to keep this mechanical component behaves elastically. What does it mean? It behaves in the elastic region. It's located in the elastic region. We are not allowed to have this mechanical component move to the plastic behavior. It means that we are designing this component to withstand an amount of stress that all the time should be lower than the yield strength or stress of the material. So that's why this yield strength is going to be considered one of the specifications, one of the design specifications based on which we have to design carefully this mechanical component. So that's why it could be counted like its strength of the material. This is a measure how strong is this material. If we are applying or subjecting the material into a stress which is higher than the yield strength, it means that the material is going to move to the plastic region. For example, if this is the stress that is applied over the material, it is lower, it is down with respect to the yield stress, it means that this is the amount of stress. If we remove this stress, the material can restore back again to its original shape. Why? Because the material, it is still in its elastic region. So once we remove the stress, this is the applied stress that comes due to the force that we are acting on the material sample, or that we are applying on the material sample. So once we remove this stress, the material can return back again to its original dimensions. So that's why we're going to say that this is the elastic behavior of the material. It can restore back. It behaves like a spring. But if we apply the stress on this material that is much higher than the yield stress, of the material at this stress level, for example, so the material will be moved to the plastic region. So that's why this yield stress, it is like a critical value. Lower than the yield stress, it is okay in terms of the design. You're going to have a good design. Beyond or higher than the yield stress, it means that your design is failed. You have a failed design or defective design, or your design is not good. Make sense? So this is a reference. This is a critical value that we shouldn't exceed. Because why? Because if we exceeded the yield stress in terms of the design, mechanical design concept, if we exceeded the yield stress, which could be known as yield strength of the material, we're gonna move to the plastic deformation. What is the problem of the plastic deformation? The problem is if we try to remove the stress, the material will not be restored back again to the zero. No, instead the material will be descending or will show a permanent shape. permanent change in the shape. It means that there will be a permanent or a new shape of the gear. Like for example, you're gonna design a gear, and because of the applied force, the gear will be distorted. There should be kind of deformation that represents the distortion, as we discussed before, in this gear. And the shape of this gear will be changed, and this shape will be permanent. It will not be in the regular form of the gear anymore. This indicates that you have a bad design. It means that we have to avoid moving the material to the plastic region. To understand more the difference between elastic and plastic, let us consider the simplest example of a stick. Assume that you already holding a stick that is made of steel or iron. And then I'm gonna ask you to bend it by hand. So simply in the beginning, if you apply, for example, if I apply a very small force over it, it will be slightly bended, right? It will be slightly bended, but once you remove your hand, what's going to happen? It will be straightened again. So it will be bended. It is completely straight without any force, right? Once you apply a force, but assume that this force is very light force, very small force. So it will be slightly bended. But once you remove your hand, it will be straightened. It will be straight one more time. It means that it will be spring back. It will be restored the original shape, which is 100% perfect straight stick. Why? This indicates that this material under this small force, under this small stress, it means that this stick is still in the elastic region. It means that at this small stress, which it should be lower than the yield stress, it means that we're still working in the elastic region, and that's why once we remove the force, it means that you remove the stress, the material has been straightened again. The stick became straight one more time. But how about if you applied a very high force that achieved a very big bend into this stick? And then if you remove your force, do you think that it will restore back again to the original shape? No, it had been highly bended. We applied a very high force that exceeded the yield stress of the material and moved the material to the plastic behavior, and in that case the material has been bended. And even if I remove my hand, it will not be straightened back again. It will be completely bended, and it will have this permanent bend all the time. It means that we are going to change the shape of this stick. In terms of mechanical design, we shouldn't allow for the change in the shape, for a permanent change in the shape of the stick because of the applied force. So we have to keep this stick operated at stress levels lower than the yield stress of the material, and we have to avoid moving the material to the plastic behavior. This is the difference between plastic and elastic. So elastic, it means that the material can restore back again to the original shape. The stick can be straightened back again once you remove the force. But the plastic deformation, the material cannot restore to the original shape. The stick cannot straighten back again upon the removal of the force. And instead, the material will show a permanent deformation or a permanent change in the shape, which cannot be restored back again, indicating that this material has been moved to the plastic behavior. Make sense? So this is simply the difference between the elastic behavior of the material and the plastic behavior of the material. Make sense? In addition to these things, we can extract some other more mechanical component, like the ultimate stress of the material. This is the maximum stress that this material can withstand. Even it had been moved to the plastic behavior, yes, but it is still an ultimate tensile stress or strength of the material that we can withstand. And this value is different from one material to other material, like steel. It has its own ultimate tensile stress. Copper has its own ultimate tensile stress, and so on. Also, the fracture point. This fracture point indicates this is the amount of elongation. This is the maximum elongation that indicates the maximum elongation that this material can experience before fracture. And this elongation gives an idea about a property which is known as the ductility of the material. How much of ductility this material has. This is the maximum elongation. For example, there are some material samples that can be quickly fractured, and there are some other material samples that can be elongated so long till it will be completely fractured. This is typical if you try to compare, for example, a rubber material, a plastic material, for example, plastic and steel. Plastic, it can be elongated with no problem, and it will be elongated so much till it will be fractured. But the steel, it will be quickly fractured. So if we compare the difference in the maximum elongation, because the amount of elongation, the amount of strain, this is the maximum strain that the material can withstand without fracture. It could be different also. It is a material property. It will be different from one material to another material. There are some material that can be strained so much till it will be fractured. This material will be known as more ductile material. These are ductile material, and we're gonna discuss the ductility. It is also one of the mechanical properties of materials. Also, but on the other side, material that can be fractured or is going to fracture quickly before showing any amount of strain, this material will be known as brittle material. So in general, there are so many mechanical properties in addition to the elastic modulus, in addition to the elastic behavior and plastic behavior, ultimate tensile stress, the yield stress of the material, the proportional limit, the fraction, the maximum strain. There are lots of mechanical properties that we can derive from this curve. How we can determine this curve? Simply do a tensile test, prepare a material sample, use the tensile testing machine, fix it over the machine, do the test, extract the figure. From this figure, you can extract so many mechanical properties. Make sense? These are some examples of the material properties, mechanical material properties, the important one that we basically gonna use as mechanical design engineer. One of the things is the elasticity, that we should have an idea about the elasticity or the elastic behavior of the material. We said that the elasticity, it is the ability of the material to restore its original shape once the applied load is removed. If the material can restore back again into its original shape and dimensions, originally the same, once we remove the applied force, this indicates that the material has elasticity. It means that the material is still working in the elastic region. It means that the applied force or the stress is lower than the yield stress of the material. Make sense? So what does it mean, elasticity? It is a measure of the ability of the material to restore its original dimensions and shape upon the removal of the applied force. But plasticity, it is a different thing. Plasticity, it means that it is the disability of the material to restore its original shape when the load is removed. The material will not be able to restore its original shape and dimension one more time. And instead, the material will have a permanently formed into another shape, or will have a permanent deformation or a change in a shape or a completely new shape after the removal of the force. If we remove the force or we didn't remove the force, we gonna end up with a new shape, and in that case, we cannot restore the original shape one more time. This, what does it mean? Plasticity of the material. Hardness, it is some of the mechanical properties. What does it mean, hardness? Hardness, it is the material ability to withstand indentation or the material resistance to the penetration of other material through its surface. To understand hardness, let us consider these two examples. Assume that you do have two plates, two slabs or plates. One is made of steel, and you do have another identical plate but made of wood. And assume that this is made of wood. And assume that you're already holding a nail and a hammer. So if I ask you to hammer the nail into the wood, so the nail will be simply penetrating into as you hammer over the nail, right? It will be simply and easily penetrating into the wood, into the piece of wood. No problem, right? But if we use the same hammer and the same guy and the same nail, and we try to nail or hammer the nail into the steel, do you think that is going to penetrate and it will be nailed into the steel? No. Why? Because the steel has high hardness than wood. So hardness is a measure of how easy or how difficult is penetrating or indentation. It means that other object is going to penetrate through the surface of this material, or nailing a nail into the, or fixing a nail into the wood or the material itself. So the nail can be easily penetrated into the wood through the surface of the wood to proceed and fix it into the wood, but it will not be that easy for the steel. So we're gonna say that the steel has more hardness than the wood. Wood, it is a weak in terms of hardness, but steel is strong or preferred or better in terms of hardness. Why? The nail cannot penetrate its surface for the steel, but it would be easy for it to penetrate the surface of the wood. So hardness, it is the material ability to withstand indentation in general. What does it mean indentation? It means that the material, or this indicate also the material resistance to the penetration of other materials through its surface. This is what does it mean hardness. Toughness is another measure. Toughness, it is the ability of the material to absorb energy. So as you can see, elasticity, it is the ability of the material to do something. Plasticity, it is the ability or the disability of the material to do something. Hardness, it is the ability of the material to do something. The toughness, it is the ability of the material to absorb energy and plastically deform without fracture. So it is the ability of the material to absorb energy and plastically deform without fracture. So what does it mean this? For example, to understand the toughness, let us assume that you're already handling two balls. One is made of plastic and the other ball is made of glass. And this is made of plastic. For example, like small game balls, one is made of glass, the other made of plastic. And for some reason that you're gonna try to throw over a very rough and solid wall, you're gonna throw the glass ball. What do you think? It will be completely fractured. Once it hits to the wall, it will not be bounced back again, right? No, it will be completely fractured and it will be fractured completely over the ground. But how about the plastic ball? The plastic ball, if you hit it to the ground, it will bounce back and it will return with no problem. And you can bounce it and you can hit it to the wall or to the ground one more time, no problem, right? So what does it mean this? It means that there is a difference. There is the difference in the impact. This is like this impact force, like you hitting to the wall, this is like kind of impact, two objects together, right? So there is some kind of energy, like throwing the ball onto the wall, and this impact, it requires energy. So there are some energy that comes because of the hitting to the wall. This energy, it is perfectly absorbed by the plastic ball. And even the plastic ball, it has been, because if you try to hit and you imagine how this ball is going to bounce over the wall. So initially the ball will hit to the wall and it will be like deformed plastically, then it will be completed back again and it will be rebound, right? It will bounce back again from the wall, right? So it means that the plastic ball, it has the ability to absorb this impact force without fracture, and even it could be plastically deformed without fracture, but it will be without any fracture and it can bounce again, or even if it has been plastically deformed, no problem, it will be counted that this plastic material has more toughness than the glass material. Glass has almost zero toughness in that case. Why? Because it can be easily fractured without any plastic deformation. Once it hits or touches the wall, it will be completely fractured, indicating that it has almost zero toughness or very weak toughness in comparison to the plastic material. So this difference, even in the absorption of the energy, the ability of the material to absorb energy, it is a measure known as the toughness. There are some material with a good toughness, there are some other material that with low or weak toughness. The toughness is also a key condition or an important mechanical property that we should consider as a mechanical design engineer. Because for example, if we're going to talk about the gears, it could be subjected to some sudden loads and abrupt change in the direction of rotation. So this is like a sudden application of fluid. This requires a material with a good toughness. It means that the gear, it should be made with a suitable material that has a suitable value of toughness, so it could absorb this, could give the material ability to absorb energy without any fracture. So this is known as the toughness. It is also one of the mechanical components. Make sense? Right, ductility also is another measure which could be compared by the brittleness or brittle, like this is the ductile material and brittle material that we just discussed. Simply, we can understand ductility as the material ability to easily deform without friction. It is kind of similar to toughness, right? But toughness is required that the material absorb energy. Toughness, it is measured by the ability of the material to absorb energy. The same thing for ductility, by the way. It is kind of related to the toughness. So it means that we should expect, as long as the material has a good toughness, it means that the material intuitively is going to have like kind of a good ductility in the meanwhile, right? But anyway, the ductility of the material, we can understand it that the material could be easily deformed without fracture. Examples of these materials that with high or excellent ductilities are rubber materials, plastics, steel, copper, and aluminum. For example, if I handle you a stick that is made of rubber or plastic, and I ask you to bend it, it will be bended, no problem. You can even keep on twisting it, right? With no problem, and it will not be fractured. Even once you remove your hand, it will be restored back again. This is the elasticity thing. Don't mix between the elasticity and the ductility. The ductility is just simply related. How easy can we deform or change the shape of the material without any fraction? This is known as a ductility. If it is easy, so we can say that this material, it is more ductile. It is a ductile material. But if it is difficult to do so, it means that this is a brittle material. To understand the difference between ductility and brittleness, because the brittleness, the material easily breaks with no deformation. Examples are glass, cast iron. Glass, for example, if we decided to compare the glass to the rubber, assume that you're handling two sticks. One is made of rubber, one is made of glass. Then I ask you to bend the stick that is made of glass. Do you think that is going to bend? No. If you try to bend it, it will be completely fractured without any bending, without any deformation. So this indicates that the glass, it is a brittle material. So brittleness, it means that the material will be easily fractured without deformation. If we try to deform the material, it will be fractured instead of being deformed. Like a typical example of this is the glass. If you try to bend any piece of glass, it will not be bended. It will be fractured instead. But if you already handling a rubber stick, and if you try to bend it, it will be bended with no problem. Even you can twist it, you can do whatever you want, and without any fracture or cutting of this rubber, and it's okay. It means that the rubber, it is a very flexible, very ductile. So we can understand even ductility, like kind of flexibility in the material, that this material, it is flexible material. Like for example, if you do aluminum, copper, steel, these are ductile materials. How? Copper or aluminum, all electrical wires are made of copper and aluminum. All of them, either copper or aluminum, right? You can, if you do have a piece of electric wire, you can simply twist it and even weld two pieces of electrical wires together by twisting them together, right? And they can be bended without fracture to the wire, no problem, right? So this indicates it is a ductile material. But can we do this twisting to a piece of glass? No. Cast iron, it is one of the iron material. It is a metallic material, but it is a special type. It is cast iron. It is an iron alloy that is brittle. Brittle, it means that if we try to bend it or do whatever, any deformation, it will be completely fractured instead of being deformed. So this is the difference between ductility and brittleness. We discussed the yield strength. We said that the yield strength, this is the yield stress point. This is the amount of stress at the yield point of the material. This is what distinguishes the elastic from the plastic region of the material. And our purpose as mechanical design engineer is to try to avoid reaching the yield strengths of the material. We have to keep our mechanical component working at a stress levels lower than the yield strengths of the material. Otherwise, the material could be moved to the plastic deformation, which will be counted as a failure in our mechanical design. So yield strength, it is the stress at which the material starts to plastically deform. This is the transition. At the yield stress, the material will start the plastic deformation, and at the yield stress, the material cannot restore its original deformation or shape one more time. The tensile stress, this is the maximum. We said that the tensile strength, this is the ultimate tensile stress. So UTS stands for ultimate tensile strength or ultimate tensile stress of the material. This is the maximum stress that the material can withstand, and this is the stress at the necking. If we can refer to this figure, this is the ultimate tensile strength of the material, or the ultimate tensile stress. But this stress value at the yield point, this is the yield strength of the material. So what is the yield strength? This is the stress at the yielding point. And this is the stress at which the material will start the plastic deformation. This is the stress at which the material will not be able to restore its original position or dimension one more time, and this is the initiation of the plastic deformation. But the ultimate tensile strength, this is the maximum stress that the material can withstand before fracture. Make sense? The Young's modulus or the elastic modulus, which is E, that found in the Hooke's law, we said that this E, it is the slope of the linear elastic stress strain curve. So it is the slope of the elastic line in the stress strain curve of the material. This gives the yield strength of this material. And in addition to these mechanical components, there are more other mechanical components that could distinguish one material from other material, but these are the common mechanical components that we basically use as mechanical design engineer. Make sense? So in today's video, we have discussed the tensile test in detail. Also, we discussed some of the important mechanical properties that we're gonna use as mechanical design engineer. Over the next video, we're gonna discuss the different material types. We said that these properties are different from one material to another material. So over the next video, we're gonna discuss the different material types that we are using as mechanical design engineer. And by this, we're gonna finish this mechanical design part, right? So that's it for today. And thank you so much, and see you in another video.